Hey there, we're looking at Chapter 7 this week, and Chapter 7 is called Quantitative Composition of Compounds. So once again we have this word quantitative again. It's been a while since we've seen that, but we're studying quantities, so numbers. When we're talking about the composition of compounds, we're talking about the relative numbers of each atom present in a compound. So we're going to be measuring again this chapter. And what are we going to measure? That's the question. Before we start with that, let's talk about ways that we count in kind of the practical world. When you have a lot of something, like if I have a compound, it's composed of several molecules or ions or atoms. It's impossible to sit there and go 1 atom, 2 atom, 3 atom, all the way up to the millions that are in a compound sample, a typical sample. So how do we, in the real world, count things very conveniently when we have several of them? Well, for instance, if we're counting eggs, when you go to the grocery store to count 12 eggs, you don't go to the grocery store and count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We know that 12 eggs is a dozen eggs. So when we count by 12s, we usually say we count by a dozen. A dozen is just a unit that means 12. So it's a unit that refers to a number. When you go to the store and you want to buy tons of paper for your printer, you buy a ream of paper, you are buying 500 sheets of paper. So the unit ream, this new unit we come up with, is a counting unit that literally means 500 of something. A gross of something is 144. So once again, a gross is just a new unit that was made as a counting unit to mean 144 of something, or 12 by 12 of something. Right? So 144. So we have all these different ways that we count using new units or itemized number units in the world. So how do chemists count things that are very, very small, like atoms? Well, we have a unit that we use as well that's very similar to the ones we just described. A dozen or a ream or a gross, referring to a number. The chemists have a unit called a mole. M-O-L-E, a mole. The abbreviation for a mole, by the way, is M-O-L, the mole. And it's just a number unit, a counting unit, that basically means 6.022 times 10 to the 23rd. So if I have a mole of paper clips, I have 6.022 times 10 to the 23rd. If I have a mole of atoms, I have 6.022 times 10 to the 23rd. So this is a number that you're going to want to learn. We're going to use this counting number a lot because when you have a lot of something like atoms or ions or compounds or particles that are so small that we have so many of them, in order to actually see them, we are going to count them by the mole. This fraction that we have here is a fraction called, or this, we'll call it conversion factor. Because a mole of something is 6.022 times 10 to the 23rd of anything. That conversion factor is called Avogadro's number, after the person who described it. So Avogadro's number is 6.022 times 10 to the 23rd of anything is a mole. Whenever we want to quickly abbreviate Avogadro's number, we use the abbreviation N sub capital A. Number of Avogadro's, Avogadro's number. So Avogadro's number is going to be very important to counting small things like atoms in this chapter. All right. What are some small things that we can count using the mole? Basically, you can count anything by a mole. But because a mole is such a large number, 6.022 times 10 to the 23rd, we only usually reserve it for things that are very, very small, or things that we have very many of. For instance, we usually use the mole to count numbers of atoms in a sample. We can also use it to count numbers of molecules, which sometimes, by the way, I abbreviate molecules MC just because I quickly want to write the word molecule down. It's not a technical abbreviation for it, but I'll just use that from time to time when I just want to write the word molecule quickly. We can also use moles to count numbers of ions. If you have an ionic compound, it's got cations and anions in it, so we can count the ions. So these are all things that we as chemists use to count by the mole. Because the mole is a unit and it equals a number, and those two things are the same, a mole of anything is the same thing as 6.022 times 10 to the 23rd of something. What we're basically saying is that Avogadro's number is a conversion factor. And it's been a while since we've seen conversion factors. If you want to go look at how to do conversions, if it's been a while and you've kind of forgotten how to do conversion factors using dimensional analysis, you might want to check out Chapter 2 again as a good review. But we're going to be using conversion factors in this chapter and in the following chapters, especially Chapter 8 again. But remember, when you have a conversion factor, an equality that has two different types of units that basically equal the same thing, you can write the conversion factor as an equality also in a ratio form. So here, I've written a ratio. 6.022 times 10 to the 23rd particles is 1 mole, so over a mole. You can also write the ratio in reverse, the reciprocal of that ratio. You can write 1 mole is 6.022 times 10 to the 23rd particles. What are the particles? Remember, once again, they could be atoms, molecules, ions. They could also be formula units. What in the world is a formula unit? Well, remember that a molecule is a group of atoms that are chemically combined by sharing electrons. A formula unit is a group of ions that together make up the formula of an ionic compound. For example, if I have the ionic compound sodium chloride, and I want to know how many formula units I have of sodium chloride, the ionic compound, one formula unit of sodium chloride is 1 sodium cation and 1 chloride anion. That is a formula unit. So I don't ask for the number of ions, but the number of ions together, a sodium and a chlorine. Alright, you'll see that term in the book sometimes, so I just wanted to tell you what it meant. And we'll be using it in the chapter. Alright, so let's practice some conversions really quick. So we see that we have the conversion for Avogadro's number. 1 mole is 6.022 times 10 to the 23rd particles. That is a lot. That's a huge number, by the way. Alright, so let's practice using the conversion factor. Now remember, when you use dimensional analysis, if you're given the unit of 1, or you're given a measurement in 1 unit, and you're asked to calculate the measurement of a second unit, if you have a conversion factor that has those 2 units in it, you can cancel the first unit to solve for the second. You put the first unit in the bottom and the second unit in the top. Unit 2, Unit 2. So remember, dimensional analysis uses the ratios of the conversion factors with both units to convert from the first unit to the second unit. Alright, so let's see an example. So the first example here says, calculate the number of atoms in 2.4 moles of sodium. So we're going to start with what we're given. We're given 2.4 moles of sodium. Now we know that sodium is an element, and elements are composed of atoms. So if we want to know the number of atoms, and we're given the number in moles, then we're going to convert moles to number of atoms. 1 mole of anything, we know, is 6.022 times 10 to the 23rd of anything. So 1 mole of atoms, or 1 mole of sodium, equals 6.022 times 10 to the 23rd atoms. Okay, I'm running out of room here. I wrote too big. So notice how I set this up. I've got a mole of sodium atoms, so I put the mole of sodium on the bottom. Mole of sodium cancels the mole of sodium. Opposite the mole, I put the number that equals the mole on top. 1 mole is 6.022 times 10 to the 23rd atoms. That's Avogadro's number. So now I just need to solve the problem. I've converted to atoms. So I say 2.4 times 6.022 times 10 to the 23rd. Well, what is that? Alright, I rearranged it a little bit so I had more room this time. It equals 1.4 times 10 to the 24th moles of sodium. Does that make sense? Well, if I add 1 mole of sodium, 1 mole of anything is 10 to the 6.022 times 10 to the 23rd. So doesn't it make sense if I have 2.4 of something? That's more than 1. It's about twice as much. Shouldn't I have more than 10 to the 23rd? Yeah, here I have 10 to the 24th. So it does make sense. Alright, let's look at another example of how we could use a mole to 6.022 times 10 to the 23rd conversion factor. This question says, how many moles of HCl, so we want to know how many moles this time, are present in a sample that has 4.3 times 10 to the 23rd molecules. Alright, so here we're given molecules and we want to convert it to moles. So let's write down what we're given. 4.3 times 10 to the 23rd, and here's where I abbreviate molecules of HCl. And we want to know how many moles. So I know that there's 6.022 times 10 to the 23rd of anything in 1 mole of anything. So that means there's 6.022 times 10 to the 23rd molecules in 1 mole of HCl. So 1 mole is always Avogadro's number. So here I converted from molecules. I've got a molecules on top, a molecules on bottom, and I'm converting to the mole. So now this time I have 4.3 times 10 to the 23rd divided by 6.022 times 10 to the 23rd. I'm going to show you another trick here. See how I have a 10 to the 23rd on top and a 10 to the 23rd on bottom? I'm going to cross those out as well. That'll save me some time on the calculator. Basically, when I go to write this on my calculator, the only numbers I'll have left are 4.3 times 1, which is 4.3, divided by 6.022. And then my answer left is moles, M-O-L. M-O-L-E-S if you want to be spelling the whole thing. So what does this equal? 4.3 divided by 6.022 times 10 to the 20, or 6.022, sorry. It should be less than 1. The answer that I get with 2 significant figures, because that's how many I started with. Remember when you do conversion, the conversion factor significant figures never matter. Only the measurement, the first one you start with. So my answer shall have 2 significant figures, 0.71 moles of HCl. 0.71 moles of HCl. So that's how you use the mole conversion factor. We'll be getting to some more difficult ones in the chapter as we go. We'll be applying this with others.